I am Atif, and the topic of this presentation is multi-source domain adaptation for object detection with prototype-based mean teacher. Let's get started with introduction. First of all, in a deep learning problem, if the training data and the testing data are from different distribution, then uh, the performance of the model suffers. And the methods to solve this issue are referred to as unsupervised domain adaptation. And in the past, it has been shown that combining feature alignment and mean teacher method have shown great result. But in a real life problem, the source data might also come from different distributions. So there is a discrepancy between among the source data along with having discrepancy between source and target data. Having this kind of data can provide more robustness to the model if they are trained properly. One way to simply solve this problem of MSDA is to blend all the source data together and use an UDA method. But the issue with that is it doesn't consider the discrepancy among the source domain. For example, we can look at this diagram. Here, both of the source data are combined, and this is a mean teacher method with uh, adversarial alignment using the domain discriminator. In the state of art method for multi MSDA, the method are using domain specific subnet to store the domain specific information. But the issue with that is the growth in parameters is very rapid with the increase in source domain. Now let's get started with literature review. There are two methods in the literature right now for MSD of object detection. The first one is DMSN and the other one is TRKP. In both the method, the whole architecture can be divided into domain general and domain specific model parameters. Uh, uh, in this architecture, the initial part of the network learn domain invariant feature, while the later part learn domain specific representation. This is the diagram for DMSN. As you can see, the whole backbone of this architecture is divided into two parts. The backbone one, which is shared by all the domain, and then we have a special subnet for each of the domain. And the teacher model is obtained by exponential moving average of both the student model, and it's a weighted average. And now let's come to the TRKP. Here we have a common backbone for all the domain, but the detection head is domain specific. And instead of relying on adversarial training, they are creating an adversarial confusion by maximizing the error in the detection head if the data is from a different domain. Both these methods were able to minimize the domain discrepancy among the source domain and align the feature, but there are two major issues. The first one is that there is a rapid growth in number of parameter with the increase in source domain. The other one is that they are not considering the class-wise alignment of object category, which can be an important factor. To solve this issue, we proposed our method, and this is known as a prototype-based mean teacher for MSD of object detection. And in this method, we are using a combination of adversarial training and mean teacher. The pseudo label are generated by the teacher model on the unlabeled target domain, and a multi-domain discriminator is integrated to get the domain invariant features. And the main novelty of our work is that we are using prototypes to efficiently store the class and domain specific information. This is the architectural diagram of our work. This is very similar to the UDA method that we have seen earlier. The only difference is that we replace the domain discriminator with a multi-domain discriminator. Now it can take multiple images from feature from multiple domain and have the domain invariant representation, and also we integrated a prototype network in it. So let's look at the prototype network, what these prototypes are doing. First of all, we are creating a prototype for every for every class object in every domain. For example, for the three domain uh, of car object category, we have three prototypes, and what we are doing is that we are pulling them closer to each other. And then we also calculate the global prototype, which are calculated by averaging all these uh, domains, and we are pulling them apart. And now let's look at the loss function of our overall training. First of all, what we are doing is that we are training the model with only the source domain up to the burn up stage. We combine all the source domain data and then train the model, and after that we start our PMT training. In that, we have the supervised loss, the unsupervised loss. Here, this is on the target domain where teacher model is generating the pseudo labels, and then we have the discriminator loss, which is the cross entropy loss, and then we have the prototype loss, which is a contrastive loss, and in this case we are using cosine similarity, and then we combine all these loss together to do our training. Now let's look at the results. First, we have the cross time setting. Here, the source domain are day and night images from the BDD 100K, and the target domain is dusk or dawn of BDD 100K. When compared to the previous MSDA method, we are outperforming them by a very good margin of around 5.5 MAP, and we are also very close to the Oracle result of all combined. Now let's look at the mixed domain adaptation setting. Here the source domain are Cityscape, MS Coco and Cinescapes, and the target domain is daytime of BDD 100K. Here also we are outperforming the previous state of the art results, and still we are a bit farther away from the previous Oracle result. Now let's look at the individual component of our PMT. As we can see that by adding each of the individual component, the performance of our model is increasing. So we can conclude that every part of the network is important for the best results. Now let's look at the table where we are comparing the number of parameter with the number of source domain for our work and our predecessors. Here we can see that for DMSN and TRKP, the growth in parameter is quite rapid. In contrary, in our case, the growth is almost negligible. Now let's conclude this paper. We proposed a new method that relies on prototype to encode domain-specific information in a very efficient way, and we called it PMT or prototype-based mean teacher method. And this PMT is performing class and domain conditional adaptation using multi-domain discriminator and contrastive loss. And we also outperform the previous state-of-the-art method while reducing the number of parameters. These are some of the references, and for any question or more detail, you can visit at our poster. Thank you.